Consider a simple reaction in which reactant A gives product B. Using the differential rate equation and rate law, we can write the rate of the reaction in terms of the rate of disappearance of reactant A as minus dA by dt equal to K into concentration of A to the power n, where n is the order of the reaction with respect to A. If the order of the reaction is 0, that is, if the rate of reaction doesn't depend on the concentration of the reactant, then n is equal to 0. Substituting n by 0 in the differential rate equation, we get minus dA by dt is equal to K, or dA is equal to minus K into dt. On integrating both the sides, we get concentration of A is equal to minus Kt plus C, where C is the constant of integration. Let this be equation 1. Let the initial concentration of reactant A be A0 at time t is equal to 0. Substituting the value of A0 at time t is equal to 0 in equation 1, we get C is equal to A0. Substituting this value of C in equation 1, we get concentration of A is equal to minus K into T plus concentration of A0. Let this be equation 2. If we plot this equation on the concentration of A versus time graph, we get a straight line with the y-intercept as the concentration of A0 and slope minus K. We can calculate the value of K by rearranging equation 2. Therefore, K is equal to A0 minus A divided by T. Now let us look at certain examples of zero-order reactions. In general, photochemical reactions such as the formation of hydrogen chloride and photosynthesis are zero-order reactions. Certain enzymatic reactions and the decomposition of gaseous ammonia in the presence of platinum catalyst at high pressure and the thermal decomposition of hydrogen iodide on a gold surface are also examples of zero-order reactions. Let us now consider a first-order reaction. The reaction in which the rate of reaction is proportional to the first power of the concentration of the reactant is called a first-order reaction. Hence, in a first-order reaction, n is equal to 1. Substituting n is equal to 1 in the differential rate equation, we get minus dA by dt is equal to K multiplied by concentration of A, or dA by concentration of A is equal to minus K into dt. Integrating both the sides, we get log concentration of A to the base E is equal to minus K multiplied by T plus C, where C is the constant of integration. Let this be equation 3. Let the concentration of reactant A be A0 at time t is equal to 0. Substituting the value of A0 at time t is equal to 0 in equation 3, we get C is equal to log concentration of A0 to the base E. Substituting this value of C in equation 3, we get log concentration of A to the base E is equal to minus K multiplied by T plus log concentration of A0 to the base E. Let this be equation 4. On rearranging this equation, we get K is equal to 1 divided by T log concentration of A0 divided by concentration of A to the base E. Since log to the base e is equal to 2.303 log to the base 10, this equation can also be written as k is equal to 2.303 divided by t multiplied by log concentration of A naught divided by concentration of A. This equation can be further rearranged as log concentration of A naught divided by concentration of A is equal to k multiplied by t divided by 2.303. Let this be equation 5. If the concentration of A is A1 at time t1, then we can represent equation 4 as log concentration of A1 to the base E equal to minus k multiplied by T1 plus log concentration of A0 to the base E. Similarly, if the concentration of A is A2 at time T2, we can represent equation 4 as log concentration of A2 to the base E is equal to minus k into T2 plus log concentration of A0 to the base E. We can also represent equation 4 as log concentration of A to the base E minus log concentration of A0 to the base E is equal to minus k multiplied by T, or log concentration of A divided by concentration of A0 to the base E equal to minus k into T. Taking antilog on both the sides, we get concentration of A is equal to concentration of A0 into e to the power minus kt. Let this be equation 6. If we plot equation 4 on graph, then we get a straight line with the y-intercept as log initial concentration of A0 to the base E and slope as minus k. If we plot equation 5 on a graph, we get the graph as shown here.